chapter 5. What's first? Electronegativity and atomic radius. What is atomic radius? Well, hopefully you all know what a radius is, a measurement from the center to the outside of a circle. So atomic radius is the measure of an atom's radius. So on the periodic table, it's good enough. As we go across one row of the periodic table, what happens to our atomic radius? Do you think it gets bigger or smaller? Let's stay in this row and go across here. Our atomic radius actually decreases as we go this way along one row of the periodic table. It decreases because as you go this way, the nucleus of the atom is getting bigger. So we might have number 53, 54, 55. That's one more proton with each atom as we go. That proton is increasing the electromagnetic pull of the nucleus on the electrons that are orbiting. So if we increase the number of protons in the nucleus, as we go this way, it's going to pull on those electrons harder, making this radius shrink a little bit. So as we go this way, the atomic radius actually decreases. Okay, we have more electrons, but they decrease. Now, as we go this way along the periodic table, we're actually adding orbitals. So remember, this is 1s2, then we get 2s2, 2p6, 3s2, and I mean, it doesn't actually look like this, but this is the model we use. We'll just say this is 1s2, 2s2, 3s2, and so on. So this is the first orbital, the second, third, fourth. You can see that those electrons are getting further away from the nucleus. So that's increasing our atomic radius. So even though the number of protons is increasing as we go down, the orbital size is increasing as well. So our atomic radius is going to increase. Okay, so those are the two general trends of atomic radius across the periodic table. As you stay in a row and don't add any orbitals, the atomic radius will decrease and the atomic radius will increase as you go down. Okay, now let's talk about soap. I don't remember which chapter exactly it was in, but it was probably in chapter 4 because it was about polar and nonpolar. So we talked about methane and how it is nonpolar. This is a nonpolar molecule because all of the polar covalent bonds cancel each other out. So this will not dissolve in water. Water is a polar substance. There's very polar bonds, so much so that the oxygen gets a slight negative charge because the electrons are spending more time next to it, and the hydrogens get a slight positive charge because the electrons are not near it as much. So water is a polar molecule. The nonpolar will not dissolve in it. So when you have nonpolar dirt and oils on your hand and you want to wash them away with polar water, you need to find something to go in between, and that would be soap. It has a long nonpolar tail, and all of these will have their hydrogens associated, and then it has a hydro, so this is hydrophobic, right, scared of water, and then it's going to have a hydrophilic head. Usually a sodium. Okay, so this hydrophilic head is going to be attracted to the water. The hydrophobic tail is going to be attracted to the dirt or whatever's on your hands and make it able to dissolve and be washed away. So this is what soap looks like. It has this long hydrophobic tail and then a hydrophilic head. And remember, when we did biology, we talked about the phospholipid bilayer membrane on your cells. They have the hydrophilic heads and the hydrophobic tails. It's the same concept. It's a really beautiful design for a cell membrane. Okay, that's module 5, chapter 5. You can turn it off.